everyone understands. Yeah,
Okay, can you open the previous lecture notes?
yeah. You mean this one?
No, no, like previous video. I mean, like week 4, there
Yeah,
is interaction. Right? Yeah.
yeah. Just give me a minute. Yeah, this one.
Yeah, this one, and then
Okay.
uh, okay, uh, yeah, go ahead, go ahead.
Mhm.
Wait, wait.
Yeah.
So about some like,
Some
mm,
more.
I mean, like previous uh thing again. Yeah, wait, wait.
Okay.
Yeah, here we are like y of x equals to ax square plus bx plus c, right?
Mm-hmm. Yeah, this one.
Yeah, here, yeah, yeah, yeah. Here we are taking x equals to x naught, right?
Mm-hmm.
Yeah. So at that I mean, in this case, like we get the function. This is x square plus bx plus c is a function, right?
Yes.
When we put, yeah, when we put x equals to x naught,
Mm-hmm.
yeah, in this, like in this equation, we get when you comes to this graph.
Yeah.
So when you we will get only the like function in between x naught and x1, right?
No, we'll get the entire function. Whether it will be valid for outside the x0 and x2, that's a question. But the function itself has the domain of overall real x, right?
Okay, so I have a doubt like a x2 square plus b x2 plus c, right? So
Yeah.
in this, yeah, in this function,
Mm-hmm.
we will get the like y, I mean function in between like x1 and x2. Is it like, is the function like that, or uh,
Uh, I'm not sure if I got your question correct. So the first one is this x0. Then we
yeah,
have x1.
yeah,
Then we have x2, right?
okay,
And we have
yeah, yeah.
corresponding y0, y1, and y2 value.
Right.
Okay.
Yeah, yeah, okay, fine.
So we have three equations. One, two is for y1, x1, y1, ax1 square, bx1 plus c is equal to y0, and 3. Okay.
Okay, okay,
And we have three unknowns, a, b, c. So generally we should be able to find this a star, b star, c star, which solve these equations simultaneously, right?
okay,
So we say that f of x, which is this a star x square plus b star x plus c star is our estimated parabola, which
Okay.
definitely passes through these 3 points, and we don't know if it passes through in between points, or maybe the correct function is some higher order polynomial, and in that case we will get some error. But this is how Lagrange interpolation works. Okay.
Okay, okay, I got it.
Yeah.
So, so it is not like that, like x naught square. I mean, it gives a complete function. We just calculated those numbers a, b, c, right, in that
Yeah.
function.
Yes. Why? Because we know that at that point the values are given.
Okay,
Yeah.
okay, okay, got
Okay.
it.
Yeah.
Okay.
Any other questions? Anyone else from last week's recap? Okay, then let's move to this week. That is week number 5. Okay. So what we want to talk about this week is integration. And why are we doing integration? Because at the end of the day we are going to solve some equations, right? Differential equation of the form some dy by dt is equal to f of t. This is a very simple equation, right? But well, it depends on what f is, but in principle you can solve it as y. Well, let me write it like this: dt, and then you integrate, right? And some initial condition is given. Let's say at t0 it's y0, and at y of at time t we need to find. So we get y of t as y0 plus integral of ft dt, right? T0 t. This is how basically any differential equation will be solved eventually, right? Obviously, or not all of them are going to be this simple, but no matter what it is, we are going to do integral at the end of the day, and that's why we are interested in calculating the integral, all right, and numerically. And so how do we do that? We do it, so we start from what we had left from the Lagrange interpolation. So Lagrange interpolation. Just to quickly revise, you have some points, x0, x1, x2, all the way up to xn. And what was the formula for estimating or interpolating the function? It was this Pn of x, right? Which was given by sum over all this yj, and then some coefficients which are the Lagrange polynomials. J is from 0 to n. Alright. And then Lj, each Lj was order of n minus 1 polynomial. Okay. And we knew the formula. So first way to integrate is what I call in my head Lagrange integration. But of course the correct word is Newton-Cotes method, which is basically that approximate your function as this and integrate that function. Alright. So your fx is something like this. So integral would be approximately that. So we can write integral, which is integral of fx dx from some a to b, or how are we writing it? Yeah, a to b. So this we are calling a, this we are calling as b. Okay. And this separation between points is called h. Okay. And how many different separations are there in total? In this case we have n, okay, because we have n plus 1 points, we have n total separations. So okay, in the nodes it's m, so let me call it m. So we have m plus 1 points and m such intervals, and each of them have equal length. So we can integrate this. So we are saying it's approximately equal to this dn of x dx from a to b. So we, this is equal to, now when we are integrating, this yj is independent of x, so that can be taken outside the integral, not the summation. All right, so at what we get is something like this, cjm and yj, or f of xj. Okay, so this cjm is basically the integral from a to b of this lj of x. All right, and because we are pulling out an edge outside, so we get 1 over h. Okay, and one general formula that we always write is that integral is sum over some points, all the points, and f of xj with some weights wj. Okay, so this wj determine how important xj point is. All right, so why is it showing unregistered? I'm sorry about this. Yeah, okay. Okay, so our job is to determine wj's and maybe x's. So in this case, this is Newton codes, right? Xj's are already known. Those are where your x1, x2 are, right? So they are equally separated, and the integral is linear combination of this f of xj. Okay, and in Newton, in case of this Newton codes, wj is just h times cj, right? So that's one thing. Then you can look at the properties, and we can do examples. When n is equal to 2, it's just linear interpolation, right? Because you have just 2 points, so you have order 1 polynomial, which is just straight line. And what it means is that area under this curve, which could be any function, right? Something like this, is roughly the area under this straight line. Now that means we are not accounting for this much area and also this much, right? So this will be positive. If this function is below the linear, it will be negative. So it might happen, just due to chance, that these positives and negatives cancel, right? In that case we get exact approximation. It might happen that they are roughly similar, not exactly. In that case we might get close to zero, right? Okay, and one thing to notice is that it is same as saying that our function is piecewise constant, right? In piecewise constant, we say that in both direction up to h by 2 it's constant. This is h by 2, h by 2. Okay, and now we want area under this from a to b, so it will be this much area, right? So this will be sum of, so this is f of a, this is f of b. So the first rectangle has area of f of a times h over 2 plus Same, the second column has area of h by 2 times f of b. Okay, and if you apply the formula in case of m equal to 2, sorry, it will be just 1, right? M is equal to 1. Yeah, so just one interval. We get the same for h by 2 times f of a plus f of b. Why? Because as I mentioned, sometimes positives and negatives just cancel. Right? So we are approximating either this way or this way. Let me use a different one. So both the pink and blue one give the same area because the difference is this triangle and this triangle, and those two triangles are equal but opposite. So one is positive, one is negative. Okay, so that's the idea. And this also goes to show that this is like zeroth order, yeah, and this is like first order polynomial. So when you go from 0 to first, there is not much change in calculating the error. Okay, but when you go from first order to second order, there is a large change. In terms of m, it will be opposite, right? Okay, and yeah, let's do it for n is equal to 3. So n is number of points, which means number of uh, regions will be 2. Okay, so now we have 3 points, and then the question is that okay, our integral is going to be, let's say this is a, this is b. So what will this be? It will be a plus b by 2 because we are considering equal separations. All right. So it's going to be a linear combination of f of a, f of a plus b by 2 plus f of b, right? And times the h. And what we put here determines our scheme. All right. So if you use this formula, Newton codes, you get 1 by 3, 4 by 3, and 1 by 3. Okay. So we are giving higher importance to this one. Now why that is the case intuitively? So let's say this is changed a little bit. So earlier it was like this, right? Something like this. And now it's changed. Let's say we are changing this by epsilon. So the new area will be this. So the area that gets affected is something like this. Now let's imagine another scenario in which we are changing A. Okay, so it was like this, A, B, and now we are increasing this by some same epsilon. So earlier it was like this, now it's going to be something like this. So the change in area is going to be smaller than that one. And this is just a qualitative argument. Huh? That's why this coefficient is smaller than this one. And the same logic applies this way, right? It's symmetric. So that's basically the idea, and you will see this again and again. The middle points get higher importance than the ones on the boundary because they affect only one way, right? So that's the idea, and in fact you can do with n is equal to 4, which means m is equal to 3, and in that case integral is, well, h times 3h by 8 times f of a, then this will be 3 times f of a plus h, let me just write, and 3 times f of a plus h 2h, yeah, the last one will get f of b. So it is symmetric for a and b and a plus h and a plus 2h. Okay, so we have 4 points. So this is a, this is a plus h, a plus 2h, and this is b. which is a plus 3h. From that we can calculate what h is. It is just b minus a divided by 3, and in general it is going to be b minus a divided by m, where m is number of intervals. Alright, so this is called Simpson 1/3 rule, and this is called Simpson 3/8. Okay, if you don't understand something, or if you want me to repeat, just ask me. Okay, and one more thing, that is that for multiple points, I mean many points. Let's say we have 1,000 points. Yeah. So okay, question. What did we do when we had 1,000 points and we wanted to interpolate? Did we use Lagrange polynomial or something else? Anyone? How did we interpolate? Are- Am I audible? Or I'm audible, right?
Yes, yes, you are audible.
Okay. Then I'll go. Okay. So when you have 100 points, you don't do 99 order polynomial, right? We saw why it is bad. It gives oscillations and it goes off bounds and all of that. So what do you do is divide and rule, something like that. Divide into segments of 3, 4 points or any points. Yeah. And let's say we are choosing this 4 points, and then we calculated a Lagrange polynomial. Then again we chose another set of 4 points and calculated another Lagrange polynomial, and we made sure that it is smooth so the slopes are same, and this recipe is called splines, right? And there are multiple ways of doing splines, so you have different splines, cubic splines and whatnot. So in the same way, what we can do is when you have 1,000 points, again divide them into equal segments of equal number of points. So in this case we have 4 points, right? So it should be here. Yeah. Okay. Now in each case, since we have 4 points, we can apply Simpson's 3/8 rule, right? Then again apply Simpson's 3/8 rule. Okay. And this can be carried on for all of them. There is one caveat that you have to remember. It is that let's say we have 10 points. So then we can do. So this will be your first point. This is second, third, fourth, fifth, sixth, seventh. So at 7 it ends. Then 8, 9, and 10. So this will be your third segment. So it is complete. If you had 11 points, you couldn't use 3/8 rule, right? Well, if you insist, then you could have used up to 10, and for 10 to 11, you could use trapezoid. By the way, this is the trapezoid rule. Okay, something like that. So this you have to remember that for a given method, there has to be a constraint on number of points that you are using. For example, for this 3/8 rule, for each segment, we have 3 points, right? And then there is one extra point. So this number of points n must be of the form 3x plus 1, where x is number of segments. Okay, similarly for one third, since we have just 3 points, it will be of form 2x plus 1 or just odd number, right? Another way to write is 1 mod 3. Okay, if you are into number theory and everything, same as saying this. Alright, so that was the Newton codes, and error estimates can be given directly, well, almost, because we know the error estimates for Lagrangian, and this is just a integration of those Lagrangian polynomials, right? So we know for Pnx minus f of x was fn psi, sorry, zeta over n factorial times product over x minus xj or xi. I is from 0 to n. Okay, n minus 1 if we are starting from 0. Okay, so this was error at point x. If we want to find the total error, yeah, we are integrating this function. So the total error is going to be just integration of ex dx. Why? Because integration is a linear operator, right? So it will be just fn psi over n factorial and then integral over pi x minus xi. Okay. Okay, and whenever I write something like this, it should be understood that limits are from lower limit to higher limit. Usually we denote them by a and b. Okay. And there is one caveat. This is true only when n is even, right? And in that case, if order of n minus 1 polynomial is the actual function, that will give zero error, right? Because the derivative we are taking nth derivative, so we have terms only up to x to the power n minus 1, so all of them will get killed, right? And that's not surprising because we know that error at every point x is going to be 0, which is same as saying we are able to estimate the function exactly everywhere. So obviously we are going to be able to integrate it also, right? So that's the idea. And when n is odd, this term becomes 0. So we need to look at the higher term, which is fn plus 1 zeta divided by n plus 1 factorial and x minus xi, and there is going to be another term which will be x minus b minus h. Okay, so we have term like a plus h all the way up to b, then the next term will be b plus h. So this is that b plus h. Okay, the product will be from 0 to n minus 1 or 1 to n, whatever. Okay, so what this means is that if we have n is equal to 2, then our error is going to be f. So when it is even, it is going to be order of n. So f2 of zeta, right? And all those terms. When n is equal to 3, error is going to be, well, n is odd, so it should be n plus 1. So it will be f4 zeta. And n is equal to 4, again it will be f4 zeta, right? Of course, there are factors here, but that's why you see high improvement from even to odd and less improvement from odd to even. Okay, so this is high, this is not so high. um, Anything else in this part? No. So this is clear, right? We are going to do coding assignments as usual, and before that we should talk about Gaussian quadrature. What's the idea? Idea is that I is always given as some weight times the function evaluated at those points, right? But if we take this xj's to be fixed, then we only have n degrees of freedom or n constants to be determined. And but if we can, yeah,
Yes, sir told when n is odd, the error is zero if that points are equidistant.
yes, error
Uh,
is zero up to this order. All right. So
okay.
okay, so that's
I'm
why,
asking.
yeah, that's why you need to go to higher order. So it's not actually
Okay.
zero. It's zero only if you
Okay.
use this formula, which is not valid. Okay.
Okay.
Yeah.
Okay.
So this is the correct formula. Okay. So in this, both xj's and wj's, we are free to choose. Okay. So in total, we have this n points and n points. So total 2n things to choose, right? And how do we determine those things? We can fit order of 2n minus 1 polynomial, because how do we write 2n minus 1 polynomial? Some a 2n minus 1 x to the power 2n minus 1 plus a 2n minus 2 x to the power 2n minus 2, right? All the way up to a1 x to the power 1 and a0 x to the power 0. So we have in total how many? 2n constants. Okay, so that is the idea. And what is the conclusion? It means if we have n points, we can fit, or rather, sorry, not fit, but integrate the function exactly for order of 2n minus 1 polynomial. Earlier it was order of n minus 1, right? So we got up twice the order of polynomial, which is very good. But it comes at the cost that this exists are not determined by us, right? I mean, they are not equidistant from A to B. The algorithm will tell us what exchange we should use. All right. So uh, that was the idea, and then we looked at different kinds of polynomials to use. So polynomials, and the general idea is that polynomials are vectors. Probably most of you know how they are vectors and what it actually means, etc. But if you are not initiated, it's very easy to see, right? So when we start studying vectors, they are arrows, and one property of these arrows is that you can add these arrows to get new arrows, right? So if we have two vectors belonging to same vector space, then a plus b will also be in the vector space, and you can multiply the arrow, right? So if this is one arrow, this is twice as big. So if this is a, this is 2a, right? So some constant c times a is also going to be in the vector space. This is the definition of vector space. So let's see if polynomials can be considered as vectors. Let's write one polynomial, just random, 3x plus 5, right? And another polynomial, which could be x to the power 2024 plus x cube plus 5x. Can we add these polynomials? Yes, we can add. right? It's going to be x to the power 2024 plus x cube plus 8x plus 5. Okay, and the important thing is that this is also a polynomial. So that's why polynomials, and we can restrict ourselves up to n, order up to n. They are going to be vectors. Okay. Now vectors in themselves need not have directions and angles, etc. Right? So how do we define vector space? We define basis. So most general is if we have x and y, we say there is a unit vector along I and unit vector along j, and if there is some point which is say this we can say 3i plus 2j, right? And we like to put heads to them. All right. So now we can ask what are the bases for the polynomials. So we have a polynomial x to the power 8 plus x to the power 6 plus 3x, right? So we can say all these monomials are bases, right? So we write it as 1 times x to the power 8 plus 0 times x to the power 7, all zeros, 0 times x to the power 2 plus 3 times x plus 0 times 1, right? So these are your coefficients just like this. Okay, these I, j unit vectors are your monomials. This one. And those are the basis vectors. And now one thing that we know about I and j is that they are perpendicular. Okay, so what this means is that you can imagine some weird abstract space, alright, in which you have all the polynomials residing. So it's up to, if it is up to order 8, then it is in 8-dimensional space, right? And the basis is just 1, then this vector is x, this is x square, x cube, right? Of course it's not a physical real space, but you get the idea. Okay, and any polynomial is a linear combination of all of this. Now as I said, I and j are perpendicular. Now is x and 1 perpendicular? What does it even mean, right? So for saying that they are perpendicular, or the better word for that is orthogonal, we need to define a dot product, right? Perpendicular means dot product is 0. Okay, but this is in the language of geometry. In general, for perpendicular we use orthogonal, and dot product becomes inner product. It's the same thing, new name, a generalized name. In my head, I always think of orthogonal thing as perpendicular in some space, and inner product is just dot product. Okay, so inner product is 0, which means we need to define an inner product or dot product between two polynomials. Okay, and there are different ways to do it. So the general way is to define a dot product between px and qx as integration from px and qx from a to b, and this is your dot product basically. So this would be the first definition. Other definition could be that you have some predetermined h of x, which are the weights, right? And then depending, so this set of h of x, a and b will define your inner product space, right? Inner product space. And once you have the dot products, you can talk about orthogonality. So what we can do is start with one and then find a linear function which is perpendicular to this. Okay, this you can do because you have a definition of dot product. So you say that inner product of mx plus c and 1 should be 0. Okay, and that will give you m star and C star, right? So now you have two unit vectors, both of them are orthogonal. Then you ask for this function, yeah, quadratic, and we say that it is perpendicular to both of this, so this and this, and that generates A star, B star, and C star. Okay, and these numbers will depend on your H, A, and B, right? Of course. And this way you can continue and you can construct a space of orthogonal polynomials. So all of these are going to be orthogonal polynomials, right? By the way, we are saying that P and Q are polynomials, but they can be functions in general, right? Okay, so these are orthogonal polynomials, so we call them phi I. Okay, so if you choose H and A and B, then you get some set of phi I. So first one is what is it called? Legendre? Yeah. For Legendre, we have Hx is equal to 1. So no weight, same weight everywhere. And limits are -1 to 1, I think. Yeah. So A is equal to -1 and B is equal to 1. Okay. So then the product, dot product or inner product between this will be phi I x and phi j x from -1 to 1. And this should be 0 if I not equal to j, right? Because two polynomials should be orthogonal, which means we can write it as delta ij times some number gamma, gamma I or gamma j. You can write anything. Okay, and in case of Legendre polynomial, this gamma I was given, was it 1 over? Yeah, I don't really have it, but it's some number that is a function of I. Right, and what are these polynomials? So the first one is 1, just to give an example, and the next one is x, right? The third one is going to be 3x square minus 1 by 2, and the fourth one will be in the fourth dimension in some abstract space, and it will be some cubic function, right? So all of these are perpendicular under this weight function and limits. Okay, in the same way, what was the second one? Yeah, Laguerre. In that case, h of x is e to the power minus x, a is 0, and b is infinity, right? So and the third one was Hermite. H of x is e to the power minus x square, a is minus infinity, and b is plus infinity. Okay, so why bother doing all of this? Because we want to evaluate integrals of the form h of x fx dx, right, from a to b. So and we know in physics it's very common to find h of x as e to the power minus x or minus x square. Yeah. So and if we don't have this factor, then it's just integral of f of x. Okay. So to evaluate this, we need this orthogonal polynomials. So if h of x is this, then we have Laguerre polynomial. If it is e to the power minus x square, we have Hermite polynomial, etc. And then you can derive exactly what the integral will be. So I is given by so the general formula is wj f of xj right? And we have to determine two things, xj and wj. If you give me these two things, then integral is estimated, right? So xj is going to be the zeros of phi n, where phi is the polynomials, the orthogonal polynomials, right? For given h and a comma b. So the nth polynomial in that you calculate and find the zeros. Those are going to be the xj's, right? So they need not be uniformly spaced. And the wj is given by minus an. So this is there in the notes. I'm just writing it for the sake of completeness. Phi n plus 1 and xj, where gamma n itself has the information of h. So gamma n is integral of hx phi square x dx. Okay, from a to b, and an is defined such that it is the coefficient of x to the power n in the phi n. Okay, so the idea is to see that if we have h, a and b, we can find wj and xj. Once you have this, you have the integral. Okay, so that's the idea. Anything else? No, then let's go to assignments. Any questions from this discussion? All right. Yeah. So first two questions are going to be theory. Well, it's very simple but descriptive. Then we have coding questions. All right. So the first question is that Simpson's method is accurate for polynomial up to. So we know Simpson's method is for two cases, m is equal to 2 and 3, right? So n is going to be 3 and 4. N is going to be 3 and 4, right? And we know that for n is equal to 3, the error estimate goes as f to the power 4 because it is odd. And for 4, error estimate also goes as fourth differential, not f to the power. I misspoke, right? And then there are of course the factors, but this means that cubic polynomial will give 0 error. And same thing for this, because both of them have the fourth derivative as the error. Okay, so it does not matter which one are we talking about. The cubic order will give error to be 0. All right, so that's the first question. Second question: Gaussian quadrature with endpoints yields accurate integral for polynomial of degree. So we have endpoints. So as we discussed, we have how many degrees of freedom or constants to determine? 2n, right? We have all the xi's, n xi's, and wi's or j. Okay, so we can determine 2n constants. Now, what's the polynomial that has 2n constants or coefficients? It's the polynomial of degree 2n minus 1. Okay, and this is repeated many times in the notes, right? So all of us know. Rest of the problems are programming questions. So we'll do the coding. All right. So the third question, the first coding question, is write a program to calculate the approximate value of the integral x square dx from a to b using trapezoid rule. Okay, and some instructions are given, which is there in almost all of the questions, so I am not repeating later. So the instructions are that integration has to be performed over n points, and the value of n a and b is given, and then we have to round the answer up to 2 points, and most importantly we can't use any inbuilt function for integration problem, right? So even if it has some function for trapezoidal, or in general we know, right, there is a function called quad which can integrate, we can't use it, so we have to use the formula. So what was the formula, if you remember? It is just average of 2 points, right? So h by 2 times f of a plus f of b. So this we have to do for each of the segments. So let me insert a code. So let's define a function which we call trapezoidal rule at least. So a, b, and capital N, just to be consistent with the problem. Yeah. So first we need the points xj's. So x points, which will be np dot linspace from a to b, only n, right? Because we have just n points. And y points is okay. We should have some f, right? Because we need to integrate that function. So y points should be a function of x point. And h is p minus a divided by n minus 1, right? Because we have n points, so it's going to be n minus 1 intervals. Okay. And last thing, what do we want to do? Okay, it gives the answer, which is very nice, but let's see how it does. So we know that it's going to be h by 2 times the sum of all the functions, except at boundary it will be summed only once, right? So let me show you. Yeah, so this is the trapezoidal rule. Now imagine we have many points, right? We have hundreds. So here we are getting a contribution of half, right, times h. Uh, this one will have contribution of half for this trapezoid, and this will again have a contribution of half for this trapezoid, right? Similarly, this point will have contribution of half plus half, right? Because it's coming in the both direction. So all of these middle ones will have contribution of 1 or 1 times h. Okay. So our integral is going to be h times sum over f of xi, right? But these 2 points, the first one and last one, will have only contribution of h by 2 times f of xi, right? So we need to subtract the extra half that we added by mistake, right? So h by 2 f of a and minus h by 2 f of b. Is this clear? I hope so. Right, so this is I0 to n minus 1, or we can write the other way, that we have just h by 2 f of a plus h by 2 f of b, and then h times sum, but sum will start from I is equal to 1 to n minus 2, okay, because the endpoints are already taken care of. Both of them is the same. So we are saying it is h times sum of all points, but we know that for the first and the second point, first and the last point, it's only h by 2. So we need to remove that half part. So it's 0.5 times y points of 0 and y points of minus 1. Why minus 1? Because that's the last point, right? So this is our function. Okay, and now we want to evaluate it. So now we want our answer as trapezoidal rule. Okay, in bracket, first argument is function itself. Now we can write a function using DEF, the conventional way, or the other way is to write it here itself. F of x is equal to, what is our function? X square, right? Then a is equal to 0, b is equal to 2, and n is equal to 100. Okay, so this is how we write function in math, right? In Python it is slightly different, but it's the same thing. Instead of f, we say it's lambda. Okay, it's a keyword, you have to use lambda, right? We don't put bracket, and the definition of lambda x is double dot, okay, not equal to, and then you write the definition. So lambda of x is not actually the name of the function, right? Any function that you define will be this way. So it's a nameless function, but we don't really care to give it a name, right? Because we are never going to use it again. So this is the definition of function that we are putting directly inside the this function trapezoidal rule. Okay, and n is equal to 1000. Okay, and what we want is round of, yeah, so round uns comma 2. This is already given in the question. So let's see, and it gives the answer as 2.67. And what's the actual answer? Not the actual, but the entire answer is 2.6668, right? And it's this is very easy integral, right? It's just x cubed by 3. So it's going to be 2 cube over 3, and which is 8 by 3. So we can print 8 by 3 also, just to check, which is just 2.66666. So it's accurate up to third decimal place. Alright, very easy. Did everyone understand what's happening? Okay, yeah. And you can do on with pen and paper. Of course, you can do using mathematics x cubed by 3, and that will give you the exact answer. But you can do what this function is doing by your hand too, right? So for the first one, it's just 0 square. So your h is going to be 2 over 99, right? So you have 0 square h times h by 2 times 0 square plus 2 times whatever the first number is, that squared plus second number squared, etc. And then all these numbers are equispaced, so they form an epi. So you can absorb the or take common the difference. The difference is taken out, then you have just sum of squares, right? 1 square plus 2 square plus 3 square, and the formula for that is n into n plus 1 times 2n plus 1 by 6. Okay, if you do that, you can get this answer, which I had already done. So you can do it by yourself, and if you don't get it, then we can discuss this next time. But I encourage that you do it. Okay, and it's same thing as what computer gives out, because it is exactly what we are telling computer to do. Alright, so and this would be a nice question in one of those NET or GATE exam, to have 100 points and still be able to do integration. Okay, then the next question is integral of, so I'm not writing the entire instructions. From now on, this instruction follows everywhere. Don't use any inbuilt function. So integral is integral of cosine x from 0 to pi over 4 using Simpson's 3 by 8 rule, and divide the integration interval into n equal space points where n is equal to 3, 3, 3. So that's where this can't be correct, right? Because as we saw for Simpson's 3 by 8 rule, where did I write? Yeah, here total number of points must be of the form 3x plus 1. Okay, and 333 is just 3 times 111. So we can divide it in equally 111 segments, but then we should have one extra points. So we should use 334 points. Okay, I don't know. Probably there is some typo here, or maybe they meant something different, but we are going to treat total number of points to be 334. Okay, that's the closest to 333, which is of this form. Okay, so again we can define our function Simpson rule. Yeah. So Simpson 3b8. Alright, so 3 by 8. And arguments are going to be same. We need to give it a function, lower limit, upper limit, and total number of points. Now it knows what to do. X points is going to be a lane space from A to B, and N is number of points. So this is correct. And Y points are just the functions at those points. Now what will be the formula for integrating? So H is same, right? B minus A divided by number of intervals, which is N minus 1. This is the Simpson's rule for just one segment, right? First one gets 3 by 8, second one 9 by 8, third one 9 by 8, and this is 3 by 8. So if you continue for multiple, okay, maybe I can show it to you. So we have multiple segments. Each segment has 4 points, right? Like this. So this is getting 3 by 8. This is getting 9 by 8. This is getting 9 by 8. So far so good. This gets 3 by 8 from this corner, this side, and from this side it gets again 3 by 8. This one is only in the second segment. So this will have just 9 by 8, 9 by 8. Again, this will have 3 by 8 plus 3 by 8. Okay, and it will continue except the last one, which will have just 3 by 8. Okay, so this is our x0, this is x1, x2, x3, x4. There is a reason I'm writing all of this. X7, x8, right? This is x9. Okay, so in total we have 10 points, which can be written as 3n plus 1, right? So n is the number of segments, which is 3. That's why we can do it. So let's see, x0 gets 3 by 8. Then who gets 9 by 8? X1 gets 9 by 8. X2 gets 9 by 8. Then x3 doesn't get 9 by 8. X4 gets 9 by 8. X5 gets 9 by 8. Again, x6 does not get 9 by 8. X7 and x8 will, right? So this 1, 4, 7, all of this 1, 4, 7, then 10. All of this will get 9 by 8. And also 2, 5, 8. This will get 9 by 8. Now who will get 6 by 8? So 3, 6, etc. So 3, 6, 9. They will get 6 by 8. And the 0 and n, those two will get 3 by 8. Okay, so that's the idea. And we know we want to write this, right? 1, 4, 7, 10. How can we do it in Python? So we can say 1 to -1, that is towards end, and in jumps of 3. So we had learned this in the beginning, maybe first or second week, and suddenly we are able to use it, right? That's why we spent some time in learning this kind of things, right? So now we can say return. So it already gives h by 8 times y.0. So 0 gets, it should be 3. So maybe oh, I can get 3 out. It becomes 3 times h by 8 y.0. Then from 1 to, I can just say -1, right? So all 1, 4, 7, they get 3 by 8. Then from 2 to -1 in steps of 3, they also get 3 by 8. Sorry, 9 by 8, but we have taken 3 out. And then, yeah, this 3, then 6, then 9. These are these points, right? They will get how much? 6 by 8. So it's going to be 2 times this. And this I should put -2 because the last one could be multiple of 3, right? So just to be extra sure. And then minus the last one gets 3 by 8. So this should work. Okay. And for evaluating, you can just copy paste this. Alright, so instead of trapezoidal rule, we are doing Simpson 3 by 3b8, and the function, the nameless function is cosine of x, right? So we have to write np dot cosine of x from 0 to pi by 4. So np dot pi by 4 using 333 points. So it should be 334 as I discussed. Okay. So it gives the answer 0.71, which is there as one of the options. And if we print the entire answer, it's 7.707, right? So if you remember, it's 1 over square root of 2 actually. So 1 by sqrt 2 np. Yeah, so it gives the correct answer up to many decimal places. In fact, how many? Maybe 10 or something like that. Okay. Why 1 by root 2? Because it's integral of cosine of x, which is sine x. So sine pi by 4, which is 1 by root 2, right? Minus sine of 0, which is 0. So it's 1 by root 2. So quite good. Anybody has any questions? Okay, then the next question. Again, some different function is given. We have to find the integral using trapezoidal rule. So we have already done this. We just need to change the limits and the function. So let me copy this. And this lambda x is now x to the power 6 minus 5 times x to the power 5 plus 3, right? From 0, from sorry 3 to b is 5, total number of points is 1000. Oh, so it's given that n is the number of segments. So number of points is going to be 1001. Alright, not that it matters, but anyways. So let's run this and it gives -1 minus 1559, which is there as one of the options. Maybe I should take it. So this was 2.67. Yeah, it was 8 by 3 basically. This was 0.71, which was 1 by 2. And this is -1559.07. And we can do this, right? This is what, x to the power 7 minus x to the power 5, x to the power 6 by 6 plus 3x evaluated from 3 to 5. Okay, so it's going to be the 5 to the power 7 minus 3 to the power 7 minus 5 by 6 times 5 to the power 6 minus 3 to the power 6 plus 3 times 5 minus 3, which is just 6. Yeah. So as professor says, it's always a good idea to check whether our method works. So that's what I have done. This is, oh, there was a 7 downstairs. So this is the analytical answer. Yeah, and it's pretty similar to what we got. Okay, so it's working. This 8 by 3 is not needed. Okay, so we have done trapezoidal and Simpson. Okay, just use formula when it's pretty simple. And once you define a function, then you can use it for any function, right? Because function can be a function of a function. So function can be an argument, and the easy way to, or rather shortcut way to define a function is through lambda. Okay, so now we go to Gauss quadrature rule. All right. So for Gauss quadrature rule, we need two things. First, where the zeros are of the phi n polynomial and what the corresponding weights will be, right? So in all of the questions, those are already given, right? Because anyways, you can't compute using hand. So it's already given. If they are not given, then we could have used scipy dot special and gotten those. Okay, but in all of the questions, those are given. So the first one is from -1 to 1, 1 plus ax square using 2-point Gauss quadrature rule, and a is given as 2. Okay, they could have just mentioned 1 plus 2x square, but that's alright. And the zeros and the weights, xj's and wj's are given. Xj is -1 by root 3, sorry, and weight is 1. And for positive root, weight is also 1. Alright. So I've already written down those x's and w's. Now we just need to do multiplications, right? So we can say answer is yeah, np, it knows actually. So np dot sum of wj xj, right? So this will do w points times f of xj. So f of x is 1 plus 2x square. So 1 plus 2 times, not 2 times 2, 2 times x point square. This is why you should be always aware when you are using AI. Okay, it could do this kind of silly things. So 1 plus 2 x point square. So this x point is, by the way, an array, right? So it is going to square each and every element of that, multiply by 2 and add 1. That will be one more array. And that array is multiplied by this, which means it will do pairwise multiplication. And then we are doing sum. which is sum over j. Alright, and that is our answer. So let's see, it gives 3.33, which means the real answer has to be 1 over 3. Okay, which you can, 10 over 3, which you can easily check, right? It's going to be x plus x cube, 2x cubed by 3. So it will be 2 times 1 plus 1 by 3, 1 plus 2 by 3. So 2 times 5 by 3, which is 10 by 3. Okay. So I will not insult you by carrying out this integration. I'm sure you can do it, and it will be 10 by 3. And it seems like it suggests that it is doing very accurately. It's almost exact, except this truncation error. So I don't know, maybe it is an exit. That's an interesting problem. I don't know how it is able to. Maybe if you know it, or if you can figure out, we can discuss next time. Okay, so that's a problem for us. How is it able to do it exactly? Okay, seventh problem is exponential of minus x square times ax square. Again, a is 2, so this is 2x square. Don't use anything here. And the weights and points are given. Okay, it's 3 points. So for 0 we have one weight, and there is a positive and negative root, and both of them we have one weight. Okay, so I have already entered that 0, 1.22 minus 1.22 and corresponding weights. Alright, once you have x points and weights, it doesn't matter what method and how you arrived at it. It could be some black magic. Once you have the x and w, the integral is just this sum, right? So it's going to be sum of w points times function evaluated at those x points, right? So in this case, what will be our function? Will it be exponential of minus x square times ax square, or just ax square? So it depends on what polynomial you are using, right? You are using Hermite polynomials, for which this is already the weight h of x. So our f of x is just this. Okay. So this is something that we should be careful about. So this is going to be 2 times x point square. Alright, let me print this. And it gives 1.77. If we round off, if we don't round off, it's something like this, which might be familiar to you, might not be. So let me print square of the answer, and it's 3.1415, which is very familiar to all of us, right? It's pi, which means the answer is going to be square root of pi. And this you can evaluate analytically. Maybe towards the end we can do it if we have time. But it's quite straightforward, right? Once you get hang of it, if x and w's are already given, then your work is basically done. And they are always given, right? If they are not given, you just call the special function. What was it called? Yeah, scipy dot special, and import roots, Hermite roots, Lagrange, etc. Sorry, roots, Legendre, etc. Okay. Then the eighth question is exponential of cx, where c is minus 2. So exponential of minus 2x cosine x using 5-point Legendre Gauss quadrature. Okay. So Legendre polynomial, which does not have any weight. Okay, h of x is 1. So for us, this is the entire function. A is 1, b is 2, and c is minus 2. So again, I've written down the x points and w points, and I just need to copy paste this. So w points times the function. What is the function? Exponential of minus, so np dot exp minus 2 times x point, this is the exponential part, and times np dot cosine of x points. Okay, anything else? No. So this will be one array, yeah, and this is another one. Both of them will be multiplied, and that will give us the yj, which is multiplied by this wj's. Okay, so let's run it, and we get 2.35, which does not look like a correct answer. So w points exponential of minus 2x times np of cosine Okay, I'll have to check this again. Can you
What
see
about the
something?
limits there?
Sorry?
Okay. What about the limits?
Oh, the limits.
One.
Oh, okay. So you are saying
Where?
limits should be taken care of.
Uh-huh.
Yeah, you are right. The limits are 1 and 2. It should be minus 1 and 1, which means we have to first transform the problem into correct limit. Yes, what was it? The eighth one, yeah. So what we are given is 122 e to the power minus 2x cosine of x dx. Yeah, you are absolutely right. Thank you. And we need, this is x is equal to 1 to go to x prime is equal to minus 1, and x is equal to 2 to x prime is equal to 2. Sorry, 1, right? We want minus 1 to 1. So there is a neat trick for this, which is that you consider on x we have 1 to 2, right? On x prime you want to go to minus 1 to, so minus 1 will be somewhere here, right? To 1. So you want to do two things, stretch and shift. So first you calculate the stretch factor, right? So this is unit length and this is length of 2, right? So you will need to stretch by a factor of 2. So x prime is going to be 2x, and plus minus some shift. That you can easily calculate, because for 1, 2x will be 2, but you want to go to minus 1. So you have to go left by 3 units. Okay, so this is the transformation. If it's not clear, you can of course just use x prime is equal to mx plus c or ax plus b. Okay, and then put these values and you get m and c. That's the arm way. This is the Mentos Zingi. Okay, so any rate, you get an x prime, which is a linear transformation of x. So you put this, and so you can invert this, right? So x will be x prime plus 3 by 2. So this will become minus 1 to 1, yeah, e to the power minus 2x will become minus x prime minus 3, and cosine of x is x prime plus 3 by 2, right? And then d x prime over 2, right? Dx is dx prime over 2, and so we can take this 2 out and e to the power minus 3 factor out. It will be e to the power minus 3 divided by 2 integral minus 1 to 1 e minus x prime cosine of x prime plus 3 by 2 times dx prime. Okay, and this x prime is just dummy, so we can just call it x. And so now we have our function is this one. This will be our function, and these two are the correct limits. All right. Oh, I hope I didn't make any silly mistake. Yeah, okay, let's see. So our function will be exponential of minus x points and cosine of x points plus 3 divided by 2. Let me run this. Some syntax error. I should have to. And I get 0.67, which is also not correct. Apparently this 1 by 2 factor should not be there. Oh, I forgot this part, right? Outside we had exponential, the factor np dot exponential minus 3, and there was half. So 0.5 times that. Still not good. The answer should be around 0.01. Oh, I think this is a mistake, right? This should be minus 0.23693. Silly me, I wrote weight as a x point. And then I have to do here too. Yeah, so I get around 0.02. I'm still not sure if this is the correct answer. Most likely it is. If it is not, then we'll revisit this problem again. Alright, okay. So if we round off, it is 0.02. Alright. And then the next question. This we'll do again if this is not correct. Because I evaluated analytically also, and it turns out to be this much, 0.012, and it is 0.016, so probably correct. Ninth one is integral from 0 to infinity exponential of minus x, just exponential of minus x, right? Which means we are dealing with Laguerre polynomials times this function where n is equal to 5. So x to the power 5 minus 5x to the power 4 plus 3. Okay, so and the weights and nodes are given. So we can copy paste this, not this one. Here, but this will be x points to the power 5 minus 5 times x points to the power 4 and plus 3, right? Are the brackets alright? Seems like that. So minus 1.33. That is not correct again. Did I write the weights correctly?
That exponential term is not included in this case also, log erg Gauss quadrature.
This one,
Yeah,
exponential of minus x. Yeah,
yeah,
that should not be there because our f of x is just this, right?
but it's for the Hermite, no, not for this log erg.
No, for Laguerre also. For Hermite, it's e to the power minus x square, right? If you look at the notes,
Okay, okay,
yeah.
okay.
Let me do just one thing just to make sure I'm not doing some silly mistake. So we have to multiply xj's here, right? Sorry, the yj, which is a function of xj, and that function is lambda x, and x to the power 5 minus 5 times x to the power 4 plus 3. And this function should be evaluated at x points. Still some error. So the correct answer is 3, which by the way is also not given in the assignments. Uh, this is x to the power 5, right? Minus 5 x to the power 4 plus 3. So I don't know what is happening. Oh, did I run this? Yeah. So the mistake was that I didn't run this, so it was considering the previous x points and w points. Okay, maybe was that the issue here? I hope not. Oh, then it's showing 0. Okay. Yeah, I don't know about that question, but this one you got it right. It gives us 3.000 then 126. So up to 4 decimals it's correct because the correct answer is 3. We will see how it is 3. Okay. It's always a good idea to check, but you get it. And yeah, as one of you mentioned, we should not use e to the power minus x, right? Why? Because it is the weight in the Laguerre-Gauss quadrature. and the limits are also correct. That also we should check, right? It should be from 0 to infinity for this one. Right. The last question, which is the triple integration, and it is explicitly mentioned that we can use Python integrator. So, and the integration is this, which by the way is confusing because you can interpret it in two different ways, at least two different ways. One is that this is the limit for x, this is the limit for y, this is the limit for z. Okay, and the other is ulta because you have dx first. So first you do this integral, yeah, and this will be integral on dx, but then dx is from -1 to 1. So I don't know. So that's why let me define a function which is a function of z, y and x. So first we try ulta. Okay, and return this function y times sin x plus z times cos x. Now, so what's the idea that z goes the first? Okay, and now answer is TPL. So I have imported TPL quad. Quad is general for integration. If you have double integration, DBL quad, I guess, and for triple you have TPL quad. Okay, so it is going to be TPL quad of, well, it goes off. So f is what f is, right? And then we have to specify the limit. So for z it is -1 to 1, and we can, okay, why is it defining as a function? I don't know. I think we can just plainly say it is 0. Let's just run this and see. Okay, it gives some answer which I don't think is correct. So yeah, let's not use this. So the first limit is 0 to pi, then the second one is 0 to 1, and then -1 to 1. So 0 to 1 and -1 to 1. Okay, let doesn't define round. Oh yeah, so this gives an answer in form of a tuple which has two elements, the answer and the error. Yeah, so then it gives the answer, which is, I hope it is 2.0, and the actual answer it generates is 1.9999. Okay, so this is how you do triple quad. Okay, and you can, there is another way which I tried, which is doing how we do it, right? First do it over z, so that is your quad of lambda z, which is a function of z, and x, y are just constant, right? And the limits could be a function of x and y, but in this case they are not. So -1 to 1. Okay, that gives the first inner integral, then do the y integral, then do the x integral. Okay, and every time you have to put 0 here because you just want the integral, right? Not the error. Okay, and if you run it, it also gives 2. All right, so that's done. We still have to look at question number 8. Probably there is some tiny mistake, or was the transformation okay? I tried to be smart, maybe that was the issue, but we'll do that again next time. Okay, so, and let's quickly check the answer just to complete. So we had done till this fifth one. For sixth one it is integral 1 of plus 2x square, right? And that turned out to be 3.33, which was 10 by 3. Okay, so as I said, I won't do it. You might feel insulted, but we can do this one because it's fun and most of us are physics students, so at some points we are going to encounter integrals like this, which we have to do on paper, right? So this is the integral. So what we can do is define a function f of alpha, which is this Gaussian integral, right? Minus alpha x square dx, and this we have to remember, it's square root of pi by alpha. I mean, you can derive this also by going into polar coordinate and doing the integral twice, etc. It's not really difficult. But if you remember this, all of the other integrals of this form become easy. You can have x to the power 4 also or anything. Okay, and the trick is to differentiate this function with respect to alpha. Okay, so this differentiation can be taken inside because it does not, the integral is with respect to x, right? And we are doing with respect to alpha. So with respect to alpha, what will be the differentiation of e to the power minus alpha x square? So remember, alpha is the one which we are differentiating with respect to, right? So in front of alpha we have minus x square. So this will be minus x square e to the power minus alpha x square dx. Okay, and if we differentiate this, then we get square root of pi, and this is alpha raised to minus half, right? So it will become 1 by 2 alpha raised to 3 by 2. So alpha times square root of alpha. Okay, so we get integral as minus infinity to infinity. This minus and minus cancel. X square e to the power minus alpha x square as 1 by 2 alpha square root of pi by alpha. And what we want is 2x square, right? It's given. So it's going to be just 1 by alpha, pi by alpha, and alpha is just 1, right? It's e to the power minus x square. So alpha is equal to 1, which means I is equal to square root of pi. And that's what we got, 1.77. Okay, if you have questions, you can ask. This too is doable. I won't do it entirely. I'll just give you idea. So we have something like this, right? E to the power cx cosine x from a to b, and the trick is to identify that cosine x is real part of e to the power ix, right? Because e to the power ix is cosine x plus I sin x. And then this itself is real because c is real, right? So we can take real part outside, in fact outside the integral, because real parts add up. So taking a real part is a linear operator. So it becomes real part of integral of e to the power.
So
Yeah.
in that question, it is not, you have to take 5 points. You didn't consider it.
Oh, did I?
That eighth question
Yeah. Oh, you are saying I took only
was
4 points.
maybe
Really?
5 point, using 5 point.
Yeah. So I have 5 points, right?
Okay, okay. Oh, okay,
Yeah.
okay.
Yeah. Yeah. Okay. So it should be something else. Anyways, as I was saying, these types of integrals can be evaluated. So we can take real part out. So this becomes c plus I x dx. And this we can do, right? It is just, so imagine this as a real number, even though it is not, but that's alright. So this is going to be c e to the power c plus I divided by c plus I from some limit a to b. Okay. Oh, so there will be an x. So once you put b and a, then solve it. Yeah, get a number which will be some complex number, right? This will be, and just take the real part. That will be your answer. So that's what I had done later on. So this is what I had gotten. Exponential of e to the power minus 4 times 2 cos 2 minus sin 2 minus e to the power minus 2 cos 1 minus sin 1. So you can check if this is correct, and there is some mistake here also. But okay, so the answer was, because when I calculated, I even programmed it and I got the correct answer. I don't know what happened, but the answer is 0.01, right? It's close to 0.01, and that was the answer. And the ninth one was e to the power minus x to the power n. So the first term, right, from 0 to infinity. And this is, does anyone know what this is equal to? If you are doing physics, then you should remember it.
Gamma of n plus 1.
Gamma of n plus 1, right? And if n is integer, then gamma of n plus 1 is just n factorial, right? So this gamma function is okay for n not equal to integer, right? You can have fractions, negative numbers, or even complex numbers. So this is how you do analytic continuation. But that's besides the point. For natural number n, this is equal to n factorial, right? So for us, it is e to the power minus x to the power 5 minus 5x to the power 4 plus 3, 0 to infinity. So this will give 5 factorial minus 5 times, it's x to the power 4 times e to the power minus 6, so 4 factorial, and plus 3 times, it's x to the power 0, right? So it's 1 factorial. Sorry, 0 factorial, which is 1. So this is 5 factorial, and what is 5 minus 4 factorial? This is 5 factorial, right? So 120 basically, but they get cancelled. So you are left with just 3. So that should have been the answer, and we got it, right? It was 3. And the last one, I don't know how to do it. I haven't done it, but the answer turned out to be 2. Okay. So yeah, that's about it from my side. If you have any questions, please ask. Some comments. Here x is equivalent to m. It's 626. So yeah, if you ask in chat box, I cannot answer. Then so can you clarify what was this question? Or maybe they left.
That equation n is equal to 3x plus 1, where
Yeah.
in that you use x,
Ah,
that
yeah,
x is
yeah, yeah.
equivalent to
Yeah, it's m, right. So it's 3 times some number plus 1. So you can use any notation, but it's 3 times some integer plus 1. Okay.
that x gives the number of segments, right?
It's
Which
the
is
number of
which is
segments. Yes.
which
Yeah.
we denote it as m in
M.
our
Yeah, yeah.
class.
So yeah, yeah. Sorry, I created some confusion. Should have stuck to the notation, but you got the idea, right?
Okay.
Yeah. Anyone else? Okay, then let's meet next week. Same link, same time. Okay. Bye bye, everyone.